Alright, here's midterm 1, and let's get right into it. For number 1, use problem 1 for midterm 1 to prove the set of all algebraic numbers is countable and the set of all transcendental numbers is uncountable. Let's start with the algebraic numbers being countable. So let A be the set of algebraic numbers, and let B be this set right here, P of x and Z of x. And remember from midterm 1 that we proved this is, we proved midterm 1 is countable. The problem for midterm 1 is countable, or is it at? Hint. We prove that's countable, this right here, let's just say that. And then this means that P of x is a subset of V of x, which we know that's countable, and then R is algebraic. Then let P of 1 be equal to this these algebraic numbers right here, where P1 of x is in B. Then since P of 1 has n roots, that is finite, and since B is a subset of that, P1 is countable. And remember, we know this is countable for midterm 1. So then since P1 is countable, we can say that P2 is countable, and so on and so forth with P3, P4, so on. Then notice that this is countable, union with this is countable, union with this is countable, union all the way to so this is countable right here. Thus by prop 1.1.16, which says the union of countable sets is countable, then a set of algebraic numbers is all countable. So now let's prove that transcendental numbers are uncountable. That's number 3. Okay, right here. So by contradiction, let's prove by contradiction. Notice that R is given as the algebraic numbers union with transcendental numbers equals the real numbers, where A are algebraic numbers, T are transcendental numbers. And then notice that A is countable, because we just proved that they're countable, but the real number is not countable, which we proved before in class, I believe. Proposition 1.116 says the union of countable sets is countable, but A union with another countable set should mean that the R is countable, but since it's not, that must mean that the transcendental sets are uncountable. Therefore, they are. We just proved that. So now number 2. That's number 3. It's number 2 right here. Okay, take any R greater than 0 and take any C into real numbers. Show that the R ball center at C is an open subset of R. Let's show it. Suppose R is greater than 0 and C is in the real numbers. Then notice that the R ball centered at C, the R ball centered at C with radius R. Okay, yeah, I just said that. Then let X be in that inside inside the ball, the R ball, such that this is what it shows X being. This is X and it's inside that R ball. So there's an R ball, and then there is an R ball centered at X, such that Y is in that, the epsilon ball, right? There's an epsilon ball centered at X, my bad, and Y is in that epsilon ball. And then let that ball be this right here, determined by this right here. Y is in there such that this is the distance, the radius around epsilon. Or epsilon is the radius, but it's within that radius. Then let J be equal to this distance, and R minus J be this distance. Then we're going to manipulate it to show that this is inside of this right here. This is a subset of this, or this is inside of this one. Because we're trying to prove that, yeah, we're trying to prove that the R ball is an open subset of R. Yeah, okay. So then you just manipulate a certain problem, Y minus C, blah, blah, blah. You manipulate it using triangle inequality to get this right here, which shows this. And then you get the epsilon ball centered at X is in the R ball centered at C. Thus, this is an open subset of the real numbers. Then let's go on to number 3. Let x1 be greater than 1, and let xn plus 1 be equal to 2 minus 1 over xn for n greater than or equal to 2. So that xn converges, so and define its limit. So we're going to use the monotone convergence theorem to show that it's bounded below and decreasing, thus mean that it is convergent. So we want to so it's bounded. We're going to do this. We're going to do induction to prove it's for both sides. So there's the basis step where n equals 1. Then you get x2 plus 1 equals x3 equals this right here is less than or equal to 1, and also less than 2 is greater than this right here, and then 1 is less than that. So let's do the next step now. So we just prove the base step. Let n equal k, blah blah blah. Consider it. That's normal. Then consider n equals k plus 1. Xk plus 2 is greater than or less than 1, greater than or equal to 1. Then k plus 2 is equal to this. Then notice that this right here is less than or equal to 1. That must mean that xk plus 2 is greater than or equal to 1. Thus, expanded below. Then we gotta show it's decreasing. Once again, induction. Here's the base step right here. We just showed x2 is less than x1. Take x2 minus x1 and you just manipulate it. And then remember that x1 is greater than 1, so that must mean this is greater than 0. So then, because this can't be 0. So then, remember that, and then you just manipulate it. You manipulate it, yeah, my bad. You manipulate it to get x2 over x1. And then induction says xk plus 1 is less than xk, then you just manipulate it until you get xk plus 2 is xk plus 1, and then by the monotone convergence theorem, xn converges. Alright, and we're gonna show the limit. The limit exists, or whatever the limit is. We just proved it exists. So xn plus 1 equals 2 minus 1 over xn. Then you take these limits and call it L. Take the limit of this called L, the limit of that called L. So then you just pretty much just solve the problem until you get L minus 1 squared, and then L equals 1. So the limit of xn is 1. Number 4. Suppose that the sum of this and converges absolutely. Prove that a squared and converges. And then if we replace converges absolutely with converges conditionally, does this remain true? If yes, give a proof. If no, find a counterexample. So then prove and converges absolutely. So then we could say, so we know and converges absolutely. We could say that and converges to 0 because we know it converges. Then by definition, if epsilon is equal to 1, there exists an n in the natural numbers such that little n is greater than or equal to big N. So then this right here, you could just manipulate it. So then it says an is less, the absolute value of n is less than 1, which is the same thing as saying it converges to 0. So then if we multiply it by itself, notice that you get this right here. And then remember that this is less than epsilon. So thus this must be less than epsilon. Thus this must converge to 0. So thus it absolutely converges. So we just prove it converges. And then if we replace absolutely with conditionally, notice that this right here converges conditionally. But if you square it, you get 1 over n, which diverges. So it is not true. It does not remain true. And there is the counterexample right there. So number 5, finally, last problem of the semester. Let's go. Suppose that if W is a subspace of the vector space X, then W is convex. So assume W is a subspace of the vector space X, then we must mean that W is closed under addition and scalar multiplication. So then let's have X and Y be in W, and then let T be within this interval from 0 to 1. Then because of scalar multiplication, we have that you can multiply X by any scalar T, and this is in W. And notice you can also multiply Y by 1 minus T, which is in W, because of scalar multiplication. And now because of addition, you can add those two together, and it's still in W. Thus, W is convex, because this is convex right here. And there is my final. Thank you.